part 2 of the lecture, guys, and I'm going to show you the whole derivation of this formula. So here we go. So now we're going to make our substitutions, and we're going to proceed from here, right? So be careful. So once you make those substitutions, you got to put that right back into the formula and carry out its operation first. And why do we need an R squared? Remember, we convert those to polar coordinates. All right. And that's broken down to several of a couple of formulas. So you square the negative sign, doesn't matter, r and cosine r. So it'll be r squared times the cosine squared, sine squared, which reduces to 1 in a sense. Okay. So once you get that, we get a little we solve it in terms of r. So I should have made that dr, right? So it's dr respect to d theta. So it depends how you look at it, right? So we're going to evaluate that from dr from remember theta, right? D theta. And your r is looking good because that's your constant, so we don't have to worry about that. And in a sense, we go over here, part 2, and we know what we derive, guys? Area of the circle. So we got pi r squared. After all that derivation, we derive the area of that circle, which makes sense because that particle is generating that region. So that's why it's important to know Green's theorem. So this is part of that. What's being manifested. The math is just so beautiful, guys. That's why it's so important. We know this works, right? It's self-evidence. So I designed this problem so you guys can understand what's going on here. So I'm letting my tell you can't understand this. Well, you can. You got to practice this, right? So we'll talk about the procedure, how to solve this problem. All right. So you guys get a good handle on this. All right, guys. See you later. Thanks for joining me. Bye-bye.